Professor's fine, thank you. Yeah, about 2 weeks ago. That's about right. Oh, good morning to you as well, and thank you. Oh, yeah, certainly. I've always been interested in UFOs since I was a young teenager, and a few years ago, I had been teaching a class in astronomy and was spending some time on astrobiology, and thought it would be interesting to discuss the possibility of beings traveling here and what that would be like. So I had started researching UFOs a little bit, looking into it in a little more detail, and found some of the information compelling and interesting. And that lecture over about 2 years morphed into a 1 hour talk that I had given to our, well, actually more like a 2 hour talk that I'd given to our physics department. And the response was very positive from the other professors and the students, and I was kind of surprised by that. And I had thought that, well, this is interesting. Maybe if, we scientists learned a little bit more about this phenomenon and saw some of the interesting correlations that appear to be observed, then, maybe this should be studied more carefully. And so a few weeks ago, I was approached by our media department, the online magazine, The Conversation. They were looking for someone to write an article about UFOs for World UFO Day, which happened, I think, July 2nd, something like that. And and so they it was funny. They had, as the media often does, they kind of spun it this way. They said, we'd like somebody to write an article about UFOs and why UFOs are so interesting to people, despite the fact that there's no evidence for them. So I thought about this and I thought, well, that's not quite right. And so I came back and I said, well, I would be interested in writing an article, but I would take this different approach. And they were actually very excited by that. The editor I spoke to said, well, we took the stance that we took because we made that proposal because we expected that an academic would not look at these favorably. So, and I said, well, I don't know exactly how to look at them, but I think that, this is something that should be carefully studied. And so I wrote the article, and so far the response has been rather positive. Well, certainly I'm taking a risk, and I worried about that. I told them before actually accepting the assignment, I said, well, give me a day or two to try writing something up and seeing, so I can see what I could do. And after I felt confident that I could write something that was, pretty level-headed and careful, then I said, all right, I'm willing to try this. So yeah, but I was very pleased by the positive response. I've had many academics and even an astronaut contact me and say, this is bravo for doing this. This should be studied. We agree this should be carefully studied. It shouldn't just be laughed at. Mhm. Oh, I would agree with that. Yeah, certainly. The I think the big difficulty is that the radar systems, in those situations aren't being operated by scientists. So the scientists aren't as able to assess the equipment, make sure there's no glitches occurring and other anomalies. So I think that makes, the use of such data, difficult, but I would agree that that's evidence, yes. Well, that's a good question. Regarding um, scientists' reactions to this are very funny, and I find that curious. Especially when we see a scientist misrepresenting information about UFOs. I think that, I'm not sure what the situation is, and it probably varies from case to case or situation to situation. But some of it is perhaps from the scientists not doing their homework and not looking into this properly. Um, and 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 I'm not going to be too critical of that because the um, as a scientist, we're often working on other projects that are, much more, immediately profitable and much more interesting in some cases. So looking into UFOs is time consuming, and we also have other things to do. So that I can see that can happen. But in that case, if that's the situation, then you should be very careful about your, expressing your professional opinion. So um, I suspect that one of the problems, especially as somebody who's taught astronomy, I see that we, our society still has this very strange belief in things like astrology and, and pseudosciences like this. So one of the things that you tend to try to do as a scientist is you want to um, educate people as to the difference between pseudoscience and science. And so in the case of astrology, this is done. We'd handle this in astronomy classes quite a bit. And I suspect that for many scientists who don't know much about the UFO phenomenon, it falls rather than being a fringe science, they view it as a pseudoscience, and so your the perceived job, the job we perceive is that we have is to educate the public about pseudoscience and to not promote this. So I think that when scientists view um, this topic as pseudoscience, they then operate to basically shut it down, which is problematic because and that sometimes I think that, they take shortcuts. So the shortcut is basically, let's just shut this down. Um, and I think they sometimes get a little sloppy and misrepresent facts. Um, and, and that's unfortunate, I think. Oh, that's difficult. One of the biggest problems with something like this is that it's a phenomenon that's not controllable, so you can't control it, and it's not assured to be repeatable. So, in science we study things that you can control and repeat, and that are repeatable or that you can somehow control, and that's typically what we study in science. That's the way we verify our hypotheses. So the fact that the phenomenon isn't controllable means that it's not easy to verify your hypothesis. That, so if you've got a hypothesis that it's an extraterrestrial spacecraft, then how do you verify that? Well, you have to wait till another one shows up, and you can't control the situation in which they show up, so it's very difficult to handle things like this. A similar example that happened, about 2 centuries ago was that of meteorites, the theory of meteorites, that the idea that rocks fall from space. And this was considered ridiculous for a long period of time. And how do you prove that rocks fall from space? Well, you have to wait for one to fall, and then you have to find it. and that's extremely difficult. And it really was a big problem until I think it was around 1802, where you had a meteorite came over a small town in France and broke into several pieces. And there were many witnesses in this town that witnessed it falling into several pieces and landed in, I think it was about 4 different places in town, and started fires in each of those places. So in that case, they were able to find the rocks, and a geologists then showed up and looked at the rocks, and they knew about the geography of the region, and could easily tell these rocks did not come from this region. So, with that many witnesses in the town and having the physical evidence, that actually changed the tide, and the theory that rocks fall from the sky, or rocks can fall from the sky, became something that's accepted. So there are other examples in science where, there were hypotheses that were very difficult to validate, and that eventually it turned around. Now, if you kind of turn this whole topic on edge and imagine, well, what would it look like if we did have an alien probe or a spacecraft full of explorers come to Earth? You would have some craft, flying over some region on the planet, and probably going to be seen by somebody eventually, and those witnesses are going to come forward and describe something very strange, and nobody's going to believe them. So now you have exactly the situation that we have occurring. So it's very hard to immediately discount some of this, especially when you have when you do have data like radar data that corroborates eyewitness reports and such. So I think that I think it's worth studying. I think most UFOs that are observed are not extraterrestrial spacecraft. I think most people would agree to that. And especially cases where you have lights in the sky, those are very, very difficult. It's very difficult to assess, and I don't really find those cases very interesting. I'm more interested in the situation where somebody was able to identify the object as being some kind of unidentified structured craft. And I think that's one of the big problems, and maybe it's an unfortunate, fact of the terminology, that we have come to think of identified and unidentified as being a binary situation. and that's not precisely accurate. I'm a bird watcher, so there are there are many cases if you go through my bird watching notes, especially when I'm in a foreign country. So I was in Brazil recently, and I might have some notes that says unidentified. Well, it's not completely identified. I knew it was a bird, and I might know, okay, it's not a great blue heron and it's not a bald eagle, so I can rule out certain cases. And so something being unidentified is not black and white. And I think the UFO cases where you have witnesses who were able to, where they're able to describe the objects they saw, they recognize them as objects, and in some cases identified them as structured craft. Those I find very interesting. Um, let's see. I mean, I've been doing research in astrophysics for several years now, since before I worked at NASA. So I was a NASA research scientist for 4 years before coming to the University at Albany, and I got into the exoplanet work just after the Kepler Space Telescope started producing results. Uh, Bill Barucki, who was the PI of the Kepler project, um, he had published a paper in Science that I was reading, and the one of the figures showed light curves from the exoplanet, and I noticed some curious, there were some curves on this light curve. It was kind of curvy around the edges. Most people are interested in the transits. So basically what you do is the Kepler Space Telescope watched a patch of sky and recorded the light coming from about 150,000 stars. And if you watch how the light from the stars vary over time, sometimes you see these dips, these periodic dips occur, and these dips are from planets passing in front of the star and blocking out a little bit of starlight. And these are called transits, and that's what most people typically had been focusing on. But while I was looking at this, I could see, well, there was some wavy type behavior going on around the transits, and I realized, wait a minute, that's probably reflected light from the planet. And I thought, I bet you could use this reflected light to learn more about the planets, and you might even be able to detect planets that aren't transiting, that aren't passing in front of the star, just by looking for reflected light. So by chance, I had been giving a lecture on astrophysics, and one of our new graduate students came up to me and said he wanted to do something with astrophysics and wanted to know if I had any projects to work on. And at the time I didn't. I told him, I'm sorry, I don't have any ideas for projects right now. And he looked rather disappointed and walked away. And I was thinking about it, and I thought about that paper that I had just read. I thought, well, what if we tried looking at reflected light, and tried studying that reflected light from exoplanets using the Kepler data. And so I caught up with the student, and I said, I do have an idea. And the problem is that it's risky. It's not been done yet, and there's a chance that it might not work. But here's the idea, and I want you to go, read about this, think about it, and then get back to me to see if you want to do that. And so a couple of days later, he got back to me and said he really wanted to work on this project. So we basically took it on, and that's how that started. That's possible. I don't know what the exact numbers are, but yeah, it's been the Kepler mission was a big deal. Oh yeah, I totally agree. I think that the Kepler mission was a huge success, and I'm looking forward to some of the new missions like TESS, which is the Transiting Exoplanets Survey Satellite, and so we have several new missions coming up, which will be giving us a lot more information about exoplanets. So we're really entering a new era of astronomy where we're beginning to learn about planets around other stars and what these other worlds are actually like, which is very exciting. Yeah, I don't know exactly what the status is and when they're planning to release data, but it yeah, that should be happening soon. And Lyra, yeah. Parallel. I think that's right. I think that's correct. Yeah, and the if you hold your hand up in that region, with arm extended, basically the area of your palm represents that patch of sky that it's looking at. So the 150,000 stars that it's been studying and the several thousand planets that have been discovered all are behind your palm of your hand, which I think is really amazing. Okay, yeah. Right. Yeah, I think it's been repurposed in what they're calling the K2 mission right now. So because they had problems with some of the gyroscopes so they couldn't um, maintain the pose to watch that one patch of sky. So now they repurposed it and they're doing things a bit differently now, but still collecting data, which is great. Yeah, that's exactly right. We had the my former graduate student, the one who I'd been speaking of, actually, who got um, jump started us being involved in this. Dr. Ben Plasek, he developed this software which we call ExoNest, and that's what we basically use to analyze the data from the Kepler Space Telescope. And the Oh, I'm sorry, and that yeah, this software not only models the transits, it describes uses information about the what happens to starlight as the planet passes in front of the star, but it also takes into account the fact that you can have reflected light, the fact that the planet could be very close to the star and be very hot, so you might get thermal emissions. Um, so you can get radiation um, due to the heat from the planet. And there are two other effects that it takes into account too. That one of them having to do with the fact that if the planet's close to the star, the gravitational force from the planet can actually distort the shape of the star slightly, and you can see that affect the light that you record as well. So we can use several different effects um, to obtain more information about what the nature of these planets. Hmm. Um, Most of the data's been pre-processed. You and you can download the data from a portal which describes the format that it's in. So off the top of my head, I don't know how different the formats are from each other. There's usually at least usually small differences at the very least. So you do have to spend a little time reading about how the data is formatted and and um, and often have to reformat it a bit to put it into the form that your software is ready for. But that information's all available on the download site, so that's not a problem. Yeah, right now they're mostly written as basically as subroutines that you can insert or utilize within the main software. So each of these subroutines computes a photometric effect, which basically is some physical effect that changes the amount of light that you're getting from the star, or that system. So each one of these is written up as a subroutine, and then for additional or future effects or refinements to these effects, you would basically rewrite the code for a refinement. You would edit the code for that subroutine, or if you wanted to take into account a new effect, you would introduce a new subroutine, which you basically just link to the main program. Mhm. Oh, I think that's basically the situation that's been revealed from this data set. I think the statistics, the last time I looked at this, the statistics were that um, 1 out of 5 stars in the sky would have a planet in the zone we call the habitable zone, where the temperatures are just right to have liquid water. So I think that's really exciting, because you go outside and just go outside tonight, count out 5 stars, and one of those stars will have a planet that's within the right range to be able to have liquid water. I think, and that's amazing. No, well, the whole idea of a habitable zone is a little tricky because they by that what's typically meant is that the surface temperatures of the planets would be such that you could have liquid water. But that doesn't mean that the planet's necessarily habitable. And as you're saying, just like you're saying, there are other worlds, that lie outside that zone where you can still have liquid water and still could be habitable. So that's right. Hmm. Right. Well, I wouldn't say 100% confident. I would say that the probabilities are rather high that there's, life elsewhere in the galaxy, but like we at this point we don't know yet. So we don't really know what, how life, in what situations life can arise and how long it can last and um there's still a lot of uncertainty and a lot to learn. That's right. Yeah, it is a big step. That's true. Uh, y- well, yeah, I don't necessarily see the two as being related directly, but I do, one of the other hats I wear is I do work in theoretical physics, looking at the foundations of physics, basically why do we have the physical laws that we have and not other laws? That's one way to look at it. Where do the laws of physics come from? Why is physics the way that it is and not something else? Sure. Yeah. The I really started thinking about this because when we learn physics, we learn you're taught about a set of concepts. You have position, velocity, energy, mass, momentum, things like this, and these are all empirically defined concepts. So you know if, sometimes you wonder, well, what do these things really represent? And we become familiar with them and their relationships to one another, and that's one of the essential steps of becoming a physicist. But at some point, reflecting back, I realized, well, we often talk about, say a billiard ball or an electron or something has a certain amount of energy, and we say this all the time. And one day it really occurred to me, that it really sank in, that, well, is it really right to say that something has energy? And because if you had another observer racing by in a spacecraft looking at it, they would say that it has a different energy than the energy that I would assign to it. So a lot of these physical concepts that we're familiar with are observer based. They depend on the observer. And so if something like the energy of an object actually depends on the observer, then it doesn't really represent something that the object possesses. It represents a description of the relationship between that object and the observer. And so I really started pondering, well, what is the nature of this relationship between an object and an observer, such that we use these what we think of as physical quantities to describe this? So we started playing around with toy models, trying to describe how, if we can come up with a very simplified picture of what could be going on and see if we can drive the laws of physics this way. So we came up with this model. We're not calling it influence theory, this idea that things influence one another, and we're looking to see how one could possibly describe the fact that things are influencing you as you're an observer in the universe. And we've been able to show that, with this very simple model, that you can actually derive some of the laws of physics this way. Basically, that the laws of physics that we've been able to work with here basically are just describing your relationship to the rest of the universe. And so I think that this is a very different perspective, and it's very new, and we're still making developments in this direction. But it's a different way of thinking about the physical laws. It's not that, from this perspective, it's not that you have laws of nature and you have energy and momentum and these physical concepts that are somehow important. It's instead that, these concepts are actually descriptions, are optimal descriptions of how things interact with each other. And so far, it's been pretty successful. Sure. Yeah, that's related to this idea, and what we were able to do in one paper that I wrote with one of my former graduate students, Dr. Nusha Bahraini, and we were looking at how an observer would be able to mathematically describe events that are happening, that are causally related. And we were able to derive the mathematics of relativistic spacetime, the spacetime that Einstein had come up with. And we were able to show that that's the only way an observer could possibly describe such events. And so that was kind of exciting and strange, because we realized that the implication was that space and time need not be physical things, but were basically just a description of events. And so in some ways, I guess this is a pun, in some ways this changes the landscape of how to think about space and time. And so one way to think about it is that, if you look at something on the other side of the room, you're basically thinking about it as being at the other side of the room, but what that is really representing is your relationship between you and that object. And your relationship between you and something far away is different than your relationship to you and something close by. And so this concept of closeness or far away, or of distance, is really a way of describing your relationship to things. So it's a different perspective. And so with a different perspective, now can ask more interesting questions. Well, let's say we take so if this whole idea of way over there is really just a description of something, well, then maybe how do you then think about motion? What does it mean to move from one point to another? Well, what you're doing is you're changing your relationship to objects. And so, what does that tell you about motion is an interesting question that we've been looking at. So I think it's a new perspective. It's so far it's been successful, and whether the theory can continue to be successful and will continue to work remains to be seen. But that's something that we're working on. So. Oh, well, yeah, this is kind of difficult. I try to avoid talking about specific cases for a simple reason. Usually, if I pick a favorite case or something that I found to be compelling, um, it doesn't take very long until somebody jumps in and says, "Oh, look, but so and so debunked that case." Well, what does that mean that so and so debunked that case? And so, and very often I've gone back and looked and see how so and so has debunked the case, and the proposed explanation, the proposed prosaic explanation is very often kind of ridiculous. So I'm never sure what to make of this. Um, I think that maybe I can talk a little more generally. I think there are cases where you have, especially if had pilots or multiple pilots, have seen large objects. And some of these objects are very, perceived to be very large, in some cases ranging from 300 feet to 800 feet or half a mile across or something like this, various descriptions. Now, as a scientist, I would ask myself, well, you would be tempted in saying, well, how do you know, judging distances or sizes at distances is a very difficult thing. So how do you really know it was a half a mile across? So that's an easy thing to say. Of course, they don't know precisely that it was a half a mile across, but in a lot of my research, I deal a lot with uncertainty. So really the question to ask is, well, how wrong could the person be, right? And so now here, let's say we have a pilot who estimates the size of this craft as being 300 feet across. Well, how wrong could the person be? I don't know. And it depends on the situation. But when you have a pilot that says basically that I looked out the front window and all I could see was this craft, well, they're not that wrong. I mean, the thing's obviously large. And so I find those cases interesting. Clearly in those cases they saw something that was large. Whether large is 100 feet across or 300 feet across, I don't know, but you know it's bigger than zero, which is then interesting. So I find those cases interesting. The other case I find interesting was where you have descriptions of the the motion of the craft, where you can make some inferences about the rates of acceleration, and especially in cases where you have this corroborated by radar data. So there are a few cases where you can make estimates of the accelerations of these objects, and they range anywhere from, I found them to range anywhere from 40 g of acceleration, 40 times the acceleration of gravity, to in one case up to over 1,000 g of acceleration. Now, and that's insane. That's an insane acceleration. And 25 g would kill a person. Yeah, almost nothing biologically is going to survive 25 g. Yeah, so now some of these UFOs are accelerating at 100 G or 1000 G. Well, of course, now you ask how wrong the person could be. So, and so some cases I basically went through and said, well, they're probably within 10% here or 50% there, and you can actually redo the calculations and figure out what the uncertainties are. So, but still, these accelerations are large. So you might end up with, well, the thing accelerated anywhere between 30 G and 70 G, of acceleration, but that's still a crazy acceleration. And so what I like to ask is, as a scientist, it comes down to testing hypotheses. So if I'm going to test this hypothesis that it's an interstellar spacecraft, well, what do I expect an interstellar spacecraft to be able to do? Well, you better be able to accelerate rapidly, and at least, and so because you have to get up to high speeds if you're going to get anywhere within a reasonable period of time. So it's very easy to sit and say, well, would 100 G of acceleration be something reasonable for an interstellar spacecraft? Well, so you can actually do those calculations, and so the the result is if you were to accelerate at 100 G, which would of course kill you, but so I don't know physically how anybody would pull this off, or it probably would destroy most equipment that we could make as well. But if you could do that, which would be an engineering problem, then you could um, literally traverse the galaxy, one side of the galaxy to the other, in about 120 days ship time. So the idea that what's basically be happening is that when you get up to very high speeds, relativity works with you as the traveler. Relative to the rest of the galaxy, your time is going more slowly, so you can actually traverse great distances in short periods of time, for you. Um, so so imagine you have a ship that takes off at 100 G and accelerates halfway and then decelerates at 100 G the rest of the way and makes it to the other side of the galaxy. Um, the inhabitants of the ship, their clocks are going slower with respect to the rest of the galaxy. So the rest of us looking at the ship would see that they could do it in about 4 months their time. Whereas for us, it would take about 150,000 years for them to do this. So, so this is why in science fiction spaceships don't just go fast, because if you could accelerate at 100 G and race across the galaxy and then turn around and come back, by the time you got back, about 300,000 years will have passed on Earth. And even though for you the round trip voyage would just take something like 2 times 4 months, which would be 8 months. So you could make the trip in less than a year, but 300,000 years would pass on Earth, and of course you wouldn't be able to see your loved ones. Probably America wouldn't be here anymore. most of the countries, most of the That's exactly it. Or there might not be TV shows at all anymore, or there might not be people. And so that doesn't make for a very good science fiction story, but what it does highlight is that the physics doesn't stop you from traveling through interstellar space. Um, there's Yeah, you can't share your information with anybody, so you can't tell anybody what you found on the other side of the galaxy. Now, of course, there are a whole set of engineering problems. How do you continue to accelerate at a rate like that? How do you survive accelerating at 100 G? How do you? Well, you can do it at a comfortable 1 G, and you could traverse the galaxy, and it would take you a bit longer, but you could do it within your lifetime. So, but how do you keep accelerating a spacecraft? Our technology works by throwing hot gases out the back, right? And so conservation of momentum is what moves the craft forward. But eventually you run out of stuff to throw out the back of your ship, so you run out of fuel. So we can only accelerate for short periods of time with our technology. And then the other huge problem is that as you're racing through intergalactic space at close to the speed of light, space isn't empty. You've got about one hydrogen atom per cubic meter, so you're going to be, and of course, relativity. From your perspective, relativity is going to shorten distances. So all of this hydrogen gas is going to be compressed, and you're basically flying through a hydrogen cloud at close to the speed of light, and that would tear your ship apart in short order. So there are, while there are some enormous and difficult to imagine engineering feats that you'd have to accomplish to do something like this, it's important to recognize that the physics doesn't stop it from happening. There's no law of nature that says this is impossible to do in your lifetime. And so I find that interesting. Now then you can go a step further and you can imagine, well, let's assume that you have a civilization that pulled this off, that could do the engineering. So you've got a bunch of people or beings that are traveling across the galaxy at these very high accelerations and very high speeds. Well, they can't go back home because they go from one side of the galaxy to the other and come back, and 300,000 years will have passed. So you literally will have, the only way you could do it is to form a breakaway society of travelers, where you have beings that they travel the galaxy, and that's what they do. And they don't go home. If they're clever, they could meet up with their friends as long as their friends keep traveling. So I'm going to go to this side of the galaxy, you go to this side of the galaxy, and we'll both meet back here, in 9 months. And we could arrange that. And if we do it right, when we meet back here, you can tell me what you found, I can tell you what I found, and it'll be 300,000 years later, but we don't care. We'll just keep traveling. And so you could end up with this society of nomads, nomadic explorers, where that's what they do. They just explore, and I don't know. I think that would be quite fun. But then it also would change. It would be that, we often think that an technologically advanced society would have a very different perspective of things, and that's true. But if you had somebody who was traveling, performing interstellar travel in this way, they're basically racing forward into the future constantly. So their perspective of things would be very different than somebody who lived on a planet. Basically, everything becomes ephemeral, and so I can imagine, so when I hear people say, why don't aliens land on the White House lawn? And my whole thing is, what's the point? Why bother? Because the next time you come back, it could be 300,000 years later or something, depending on how far you travel and how, where you're going to and what your plans are. So I think that I think it really is true that it's hard to imagine what the perspective of an interstellar traveler would be. But I think it's important to realize that you don't have to go faster than light to do it. But there are huge engineering challenges that one would have to face. Yeah, I still think it's a hard limit. I think that, for a few reasons. First, there's nothing in that. There's no experiments that have been performed that suggest that you can break this limit. And the theoretical work that we've developed reproduces Einstein's work on relativity. So which says that the speed of light's the limit. So I think that that's correct. Well, of course he was a genius. Yes. Yep. It warps space-time according to relativity. Yep. It could. It depends on, yeah, it depends on what ideas we would possibly have that we could capitalize on, but I wouldn't rule it out. No, I think we've covered most of the topics. Oh, thank you very much. Yes, several. So this is my second one. I did the API case files last night. So no, not at all. I love my day job and I love looking at exoplanets and I love the theoretical work we're doing and it's very exciting. So, yep. All right, thank you very much. Thank you for having me.